introduction. Thank you all for coming here. To those who are regular attendees of the Journal Club, if you didn't know this was happening, this is a special Journal Club. I use my organizer privileges to take this slot from but we also have more food available, so please feel free to. The title of my thesis and the title of this defense is The Holography of Boundaries in Quantum Gravity, because I figured that that title would best encapsulate a fairly large swath of the work that I did in grad school that was very formative in my own development. So let me start by giving a little bit of a sense of the big picture, especially for the benefit of the general audience here. So first, what is quantum gravity exactly? So to answer that question, it helps to look to two of the most well-established theories of 20th century physics, which are general relativity and quantum field theory. So general relativity is essentially the physics of large things, and in particular, it's our best theory for thinking about just gravity as a force between objects. In particular, thinking about how objects will curve space-time, and that will make objects interact with each other through this force. But then there's also quantum field theory, which is more about small-scale physics, like atomic scale physics, for example. And that's how we can think about things like electromagnetism or the weak and strong nuclear forces. In particular, we tend to apply that in a regime where gravity is much weaker than those other things, so we ignore gravity. But we live in a universe that presumably runs on one set of rules. And so a theory of quantum gravity is really a more complete theory that includes both of these other frameworks in the appropriate limits. And you might want such a theory to think about scenarios where you're breaking some of the assumptions at which these theories are good. Like, for example, when you're near classical singularity in general relativity, like deep inside a black hole or near the very, very early part of the universe. So what are some features of a theory of quantum gravity? Well, the main one that I'm interested in is holography, or the holographic principle. And the story here starts with the Bekenstein-Hawking entropy formula, which was this formula that came out of this endeavor from the 70s to treat black holes like they're thermodynamic objects. So you can characterize them by some sort of temperature and energy, and in particular some sort of entropy that counts the number of degrees of freedom of such a black hole in kind of a coarse-grained way. Now normally, the entropy of an object you might expect would scale with the volume, so it would be extensive in the bulk size of that object. But the result of Bekenstein, which the prefactors were fixed by Hawking, is that the entropy of a black hole actually scales as the area of the event horizon. And so black holes, even though you can think of them as like being these 3+1, 3 space, 1 time dimensional objects in gravity, for example, such a black hole actually seems like more of a 2+1D object because of Bekenstein-Hawking. And so this kind of paves the way to the holographic principle, which is, but at the time it was quite a radical interpretation of Bekenstein-Hawking, where you think of a d+1 dimensional theory of quantum gravity as being, in some sense, equivalent to a d-dimensional d-dimensional quantum field theory. Now, the most concrete manifestation of that comes from string theory, which is our best theory of quantum gravity, and it's called the ADS-CFT correspondence. It was really demonstrated in great force by Malvicena, but there were kind of bits and pieces that were shown before that. And generally, ADS-CFT by this point has transcended the technology of string theory. Like, people use it in certain classical limits instead now. But the basic statement is that gravity on d+1 dimensional anti-de Sitter spacetime, or ADS, is equivalent to a lower dimensional conformal field theory in d dimensions. So what is ADS? It's a type of manifold that has this intrinsic negative curvature to it. And so basically each time slice has this hyperbolic geometry, which is usually shown by showing one of M.C. Escher's 4 circle limit prints. So essentially there's a boundary to each time slice, and as you get closer to the boundary, the distance, or really specifically the metric, will diverge. A conformal field theory, meanwhile, is a type of quantum field theory that's invariant under what are called conformal transformations. So these are transformations that loosely speaking, locally preserve your angles. And so these would be things like rotation or scale transformations. And so we call the ADS space or space-time the bulk, and we say that gravity theory is the bulk theory. Meanwhile, we say that we call the CFT the boundary theory because you can say it lives on the boundary of ADS. So ADS CFT is particularly useful as it's seen a lot of use as a test bed for ideas in semi-classical quantum gravity, which is a sort of kind of attempt at thinking about quantum gravity naively as GR plus quantum fields on top of it. It was really how people thought about it in the 70s, in particular Hawking, and it's notorious for a lot of puzzles and paradoxes, like the black hole information paradox, which I'll lay out for you later in the talk. It's also a type of strong-weak duality. So normally when we work with quantum field theories, we work perturbatively. So we might start with some sort of free quantum field theory where we don't have any interactions between the fields, and we turn on some weak interactions, and we essentially do series expansions. But if the interactions are very strong, then you can't really do that anymore. There are fewer methods available for actually working at strong couplings, like lattice or bootstrap, which are notoriously imprecise and unwieldy. But ADS-CFT is another one where you can use general relativity on ADS to probe the physics of a strongly coupled lower dimensional conformal field theory. So now let's talk about extended objects. This is a catch-all term for basically any object that has finite or even infinite size. So any objects that are large, like boundaries, strings, defects, and these are non-perturbative because they have some finite size. You don't treat them as being small. In string theory, the classic example is the idea of D-branes, which are boundaries on which strings propagating in space-time will end. But these D-branes have been really important in the development of string theory, particularly in the 90s, and were even the reason we were able to make the statement of ADS-CFT in the first place. So what I'm interested in is how boundaries in quantum field theory map to some gravitational theory, or some higher dimensional description under holography. And roughly speaking, this kind of branched off into two lines of work. The first was more dedicated to building up the toolkit of ADS-CFT, the so-called dictionary, and seeing how boundaries fit into that. While the second was more about using some holographic construction of boundaries to study toy models of these puzzles in semi-classical quantum gravity, particularly black hole information. So let's start with the first direction. First, let me just clarify what I mean by holographic dictionary. So ADS-CFT is a statement that quantities in one theory map to quantities in the other. We call the set of such mappings the holographic dictionary. So for example, surfaces in ADS will map to entropies in the CFT. Bekenstein-Hawking is kind of the harbinger of that, but later I'll talk about the more modern version, which is Ryutake-Nagi. Isometries of the ADS space-time, so distance preserving global transformations, map to global symmetries of the conformal field theory. They're both described by the same exact Lie group, which is SO2, and the entry that we'll focus on in this part of the talk is that both paths that go in through the ADS geometry correspond to correlation functions in the CFT. So roughly speaking, we can ask how boundaries fit into the broader dictionary. First, let me clarify what I mean by boundaries in a quantum field theory, or really in a conformal field theory. So a boundary conformal field theory, you might try to say is a CFT defined on some d-dimensional manifold with some boundary, like a disk, strip, finite cylinder, half space, whatever. But such a like when you have a boundary like that, it actually breaks some of the global symmetries of your theory. But for a BCFT, what we want is we at least want to preserve a reduced amount, or one codimension amount of conformal symmetry. So if I want a BCFT on half space, I basically want my global symmetries to be described by d-1 dimensional conformal group. And this is often enforced by imposing some sort of conformal boundary condition on the fields. in the 2D upper half plane, for example, or really in 2D, I can just define this in terms of the stress tensor, because the stress tensor is always a way to characterize a CFT in 2D. So what I would say in the upper half plane is that the holomorphic and anti-holomorphic components of the stress tensor equal each other at the boundary. So how do I think of a BCFT holographically? Well, you might want to try and introduce a boundary into the ADS D+1 bulk. And so that's what we do. So we add this thing that we add in this thing that we call a codimension 1 end of the world brane, which basically cuts off the space-time. So essentially, in the bottom left, I have some sort of half-space bulk that's cut off by this this dark red end of the world brane, and I have no space behind that. And ADS gravity on that sort of configuration is dual to some BCFT on the half-space in the upper left. Or maybe I have a very bulbous end of the world brane, which asymptotes to a disk, in which case my BCFT is on a disk. The actual positioning of the brane is not something I am allowed to really put in by hand because of different variance. So it's set by some dynamical equation instead that I get from the classical, from the action. And this end of the world brane, you would expect that this probably changes the dictionary in some sense, or maybe even gives some sort of novel entries to it. It makes it richer. So how do I actually construct these things? The usual way to do this in a bottom-up fashion is to start with the D+1 dimensional bulk Einstein-Hilbert theory with a negative cosmological constant, r minus 2 lambda, but so you get the plus sign because lambda is negative. So lambda is d minus 1 over 2l squared with a minus sign. And the L here is some length scale corresponding to the ADS geometry. But I also want to have this, so that's on this manifold M, but I have this boundary Q, which is my end of the world brane. And because I have a boundary in a gravitational theory, I need to add on a Gibbons-Hawking York term to make the variational problem actually make sense. And then on top of that, what I can then do is I can add a brane localized action that so corresponds to some sort of matter on the brane that then stabilizes different configurations of the end of the world brane via a Neumann boundary condition on the metric at Q. So that would be the equation on the lower left. So this embedding equation will determine what sort of end of the world brane I'm allowed to have. The simplest sort of thing to add is a Randall-Sundrum term where my IQ is just proportional to the world volume of the brane. T here is some coupling that's called the brane tension. And with this sort of action, the embedding equation becomes pretty simple. You can contract all the indices and get that the end of the world branes just have constant extrinsic curvature. Furthermore, in order to be consistent with this reduced conformal symmetry in the boundary theory, I want the geometry of the end of the world brane, the induced geometry, to be ADS-E, so that its isometries correspond to this reduced conformal structure in the boundary theory. And that imposes a bound on the value of T. So T has to be what's called subcritical with respect to this bound. And as an example of what one of these configurations ends up looking like when you go through and solve the equations, let's take the Euclidean Poincare metric, which I'll be using shortly. So here, the metric blows up as I go to z equals 0. So z equals 0 is the conformal boundary of Euclidean Poincare. That's where my CFT lives. And so that's represented by this white channel here. And my branes need to be these constant extrinsic curvature slices that are ADS-D. I can get that by actually there's foliations of ADS-D+1 into ADS-D slices. So for example, I could do a planar foliation, which is the thing I've written on the left, where the angle, the theta is the angle between the conformal boundary and the end of the world brane in red. Theta is really a reparametrization of the tension. And I can also, so I can supplement that action that I wrote before with some matter, either in the bulk or on the brane. So for example, I can add a scalar field. So like here I have a Klein-Gordon action, and I also have the scalar coupled to Q with some potential. The kappa phi is just some coupling. And such a scalar field would be dual to some scalar operator O that has some conformal dimension yeah, some conformal dimension delta phi that related to the mass of the scalar. Okay, so now we're ready to talk about geodesic approximation. So, so let's say that I add such a scalar to my ADS gravity theory, and I want to work in I just want to avoid certain complications due to back reactions. So I'll work in a regime where the scalar is not back reacting on ADS. In which case I can try to do scalar field theory on an ADS background and try and interpret what I get in terms of CFT. So I can compute the Euclidean scalar propagator between 2 points that are on the boundary, really on some cutoff near the boundary, but for all intents and purposes, you can think of them as boundary points. Zeta 1 and zeta 2. So this propagator G is given by a path integral, where I integrate over paths P that connect these boundary points, these boundary insertions. The path integral is up this exponential where delta phi is again the conformal dimension of the dual operator related to the mass of the scalar field, and L is some length functional that tells you what the distance of this path is. Now, evaluating that sort of integral is hard, but there's a trick we can do to approximate it in some regime. We can take the limit as delta phi goes to infinity, in which case this thing is just approximated by its saddle points, of the length functional, which are geodesics. And so instead of integrating over paths, you just sum over geodesics in that regime. And then the last step is that we can equate that bulk scalar propagator between boundary points to a scalar 2-point function in the CFT. So what we end up with is the statement that if I have the scalar 2-point function of some heavy scalar operator O, that's computed by summing over geodesics in the bulk ADS space.
I've been confused about this. I mean, is really taking delta phi to infinity consistent with the no back reaction assumption? Isn't there kind of a bit of tension there between taking the scalar to be very heavy and saying it doesn't back react on the geometry?
It's the scalar very heavy with respect, the scalar mass very heavy with respect to L, but you can still control the scaling of M with respect to G Newton. And I think that's going to actually control whether or not you have back reaction. So we try to keep, M is heavy in ADS length scale, but not
light
so
in
light in G Newton. Yeah.
And in terms of delta, you mean delta is much larger than 1, but much less than n squared, right? It's the same.
Well,
Yeah, I guess that would be the same.
Right.
Yeah,
Yeah,
that would
yeah.
be the same. Right. Right. Yeah, maybe I should be more precise, but yes, thank you. Okay, so how do I do that sort of thing with boundaries? Well, there's actually old heat kernel literature from the 90s that tried to address this question of computing propagators via path integration in the presence of boundaries, to solve the heat equation with boundaries. And what they basically argued and found was that when you do all of this, when you go through all those steps and you end up with this sum over geodesics to compute the scalar propagator, you technically need to sum over geodesics which reflect off of the boundary. And the extremization of those geodesics also demands that they obey this law of reflection. So they have to bounce at equal incident and reflected angles at the boundary. And so what you end up with is that the scalar propagator is formally this infinite sum, where the signs are either alternating or not alternating depending on the boundary conditions of the scalar field. If it's Dirichlet, they alternate. If it's Neumann, they don't alternate. So we basically apply this to the ADS plus end of the world brane set up to compute 1 and 2-point functions. And so 1-point functions, you can either use that statement of the law of reflection, or you can say, well, 1-point function should be computed, the heavy 1-point function should be computed by geodesics which start at some insertion and don't go to the boundary, but instead end on the end of the world brane. And you can minimize over all of those as well. But either way, what you'll end up with is that the minimum length is given by the geodesic that hits the end of the world brane in red orthogonally. And so you can just compute that length and plug it in. And what you end up with is that the structure of this 1-point function looks like this equation 2.12 here. Now, there might be some boundary condition dependent prefactor. Like if you have a Dirichlet condition on the scalar, for example, you technically have this but times 0, so it's just 0. But if you have other boundary conditions, like some dynamical boundary condition, then you get this times like maybe some coupling. And this equation passed several of our consistency checks. So the preliminary one is that it has the right structure of a one-point function in a BCFT. So that's good. But also there's another way to calculate the one-point function of a scalar operator by doing scalar field theory in ADS, solving for the scalar field and looking at its asymptotic behavior near the conformal boundary. So we did that as well. And in the limit of taking delta to be large in L, we got this expression back. So it seems solid. So let's now talk about two-point functions. So first I'll focus on the connected. I'll just focus on the connected part. The disconnected part is just a product of one-point functions. So it's just you just add two of those boundary to brane orthogonal geodesics. So it turns out that in ADS with this planar brane, you can show that you can only have 0 or 1 reflections. There's no actual configurations of geodesics where you have them as being locally geodesic and reflecting if you include at least 2 reflections. I don't have the argument, but basically that's something you can show from just the geometry of ADS. So we only have these two, the green one, which is no reflections, and yellow, which is 1, it's reflecting. We can, just as a technical note, we can compute this on a constant transverse slice, so constant x, and just do it on the zy plane, and rewrite everything in terms of the cross ratio, conformally invariant cross ratio, and then get our answer that way. It just makes things easier. But so if we have these geodesics, so from these geodesics, we get this form for the two-point function. The first term is the non-reflecting contribution. The second is the once reflecting contribution. The plus or the minus is boundary condition dependent. Plus means you have some Neumann or some dynamical boundary condition. Minus means you have Dirichlet. Now, those geodesics don't always exist if t is less than 0. So I kind of have a figure here where t less than 0 means this theta is an acute angle, and I have like this small wedge. So if you take these insertions to be too far apart, there's a point where the geodesic, you can try to draw the geodesic and it just won't fit in the space. So that happens when your cross ratio is too big. When your cross ratio is that big, you can then say, okay, the connected part of the two-point function is 0 in this limit, in this heavy limit. I still have the one-point function, the disconnected contribution. So this is something like a factorization phase transition, where I go from having something that is not a two-point function that doesn't factorize to a two-point function that does factorize. Okay, so kind of in summary, end-of-the-world branes do appear to modify and even append the holographic picture in very non-trivial ways. And in this paper, we examined geodesic approximation, and we also had some follow-up work where we looked at different configurations of end-of-the-world branes and saw what that did to the CFT. But unfortunately, I had to cut that because I wanted to be sure to talk about black hole information. So, what is the black hole information paradox? Basically, the general idea comes from Hawking back in the 70s. So, in this program of thinking of black holes as thermodynamic objects, you come to the statement that black holes emit thermal radiation when you have quantum fields tacked on to your theory of gravity, your general relativity. And this radiation is called Hawking radiation. It drives a black hole to evaporate. Basically, it just emits all of its energy until it just shrinks to nothing. And the end state of that process is completely thermal, so you actually you can't really get any information about the state of the black hole from before evaporation. But the problem is that in quantum mechanics and quantum field theory, time evolution should be a reversible process. This is part of those theories being unitary, and so you shouldn't lose access to information from the past, to microscopic information from the past. You should always be able to access it. So this is quite puzzling, and this has puzzled people for a long time. I'm going to phrase this in the language of entanglement. So entanglement entropy is some way of counting the degree of entanglement between a region of space and its complementary region of space. When Hawking radiation is emitted, you can then say, like, oh, okay, so then the exterior degrees of freedom of some black hole configuration are entangled with the interior degrees of freedom. So that would then make you say, okay, entanglement entropy should increase monotonically, maybe until evaporation. But from Page, we also have the statement that, well, if this process is unitary, entanglement entropy should go up until eventually it starts going down at what's called the Page time, until it continuously nicely goes to 0 at the time of evaporation. So you have this tension between these two. This plot basically is a graphical representation of the information paradox in this language of entanglement. So how do we think about entanglement in ADS-CFT? So the starting point is Ryu Takeyanagi, which is an entry of the holographic dictionary, which tells you how to compute entanglement entropy of the CFT subregion R in terms of some bulk quantities. So I call a bulk codimension 2 surface, which I'll just denote as gamma R, homologous to R. I've heard people say this is not the same homology as what mathematicians will call homology, but I'm not too sure about that. So this is the working definition that I'll be going with. So gamma R is homologous to R if the boundaries of R and gamma R are the same, and if there's some bulk codimension 1 sigma such that its boundary is R union gamma R. So the sigma would be this white space in between the gamma R and the R. And so what Ryu Takeyanagi tells us is that for some boundary subregion, I'll be careful and call this classical entanglement entropy, so entanglement entropy with no quantum fields yet in ADS, is computed by 1/4G times the area of the minimal extremal gamma R, that's homologous to R. So it's kind of like the area of some soap bubble that attaches to R calculates the entropy. And this is actually, in ADS, a generalization of Bekenstein-Hawking. If you take a black hole in ADS and you try to compute the entanglement entropy of the full boundary system, you just get the horizon back. So you get Bekenstein-Hawking back. So I said that didn't include quantum fields. There's an extension called the quantum extremal surface prescription, where you add quantum fields and you say, okay, instead of extremizing that area over 4G, I want to extremize this generalized entropy functional on the right, which includes this Sm that represents the entropy of the matter fields inside of that region sigma. So I want to minimize this whole sum. And the entropy I get by doing that, I'll call the quantum extremal surface entropy. And it's computed by some surface gamma R, which is called the quantum extremal surface. Okay, so let's apply this to black hole information. There's a thought experiment that we can do where we consider an ADS black hole that's coupled to some thermal bath. The reason I would want to do that, to think about black hole radiation or black hole evaporation, is that ADS, because of that boundary, is kind of like a box. So just an ADS black hole by itself, it might emit Hawking radiation, but that radiation will bounce right back and go back into the black hole. So we need this back to really talk about this thing that Hawking was thinking about. And the quantum extremal surface in that sort of setup was found to undergo a phase transition back in these papers in 2019, which set off a whole flurry of further work. So they basically found that at early times, the quantum extremal surface would increase in area for a while, which that's fine. But then at some time, there would be a phase transition, and the quantum extremal surface would switch to some other surface that decreased in time until going to 0 at late times, or going to 0 at the evaporation time. There's also an eternal version of this, which is what will be really useful for us here, where we take some eternal ADS black hole, and we couple the asymptotic boundaries of, it's two-sided, and we couple the asymptotic boundaries of this two-sided black hole to two bads that are in thermal equilibrium with the black hole. And we as some super observer want to collect Hawking radiation here on the right and here on the left, and compute its entanglement entropy as a function of time. And if I do that using the quantum extremal surface prescription, what I can get is that it increases for a while, and then there's a phase transition, and then it goes constant. Now, one more thing I'll note, this phase transition, before it happens, you just have like kind of a mundane surface, but after it happens, you end up getting a surface somewhere in the bulk as part of your QES that is disconnected from, it's disconnected from this radiation. So that's called the entanglement island. So this whole paradigm goes by the name of the island program. So there are three features of all of this work that are kind of undesirable, at least from a phenomenological standpoint. The first is that the black holes are an ADS. Unfortunately, holography is not as well developed in other space times like de Sitter, for example. So we can't really do anything about that. We're theorists. We work with toy models. We take what we can. But the other two we can do something about. So the initial calculations were all in 2D gravity plus a dilaton to make it not just topological. But the RS construction from before, the one using end of the world brains, that's actually a way to send this to higher dimensions. And you can actually consider, in this thought experiment, black holes that live on a Randall-Sundrum brain. The third thing is this non-gravitating bath. So it feels kind of artificial. You're just kind of attaching this bath here. And it also even when you do this RS construction to get to higher dimensions, it still persists there. And there's also a known problem in those settings where when you have a coupling between a gravity theory and some non-gravitating bath, you actually get massive gravity. So the graviton in the gravitating part picks up a mass. So this all begs the question, how does this bath maybe affect the QES calculation in higher dimensions? Does that have any sort of influence on the physics that you might not want? So let me start by just elaborating a bit on the setup. So starting with some D+1 dimensional bulk with some end of the world brain, the way we think about the black hole living on the brain, or really the gravity theory living on the brain, is we integrate out the bulk degrees of freedom up to the conformal boundary and up to the brain. And this is kind of a dimensional reduction procedure that ends up getting you an effective theory of quantum gravity in this gravitating universe coupled to this non-gravitating universe. So this part is called the brain world, and these were very popular back in the aughts, and they're still fairly popular by some crowds. So you have this essentially equivalence between the bulk theory here and this brain world theory with this bath. But there's also the equivalence of ADS-B CFT, where this is equivalent to some boundary CFT. And so going all the way from the left to the right, or right to the left, takes 2 steps of applying holography, so we call this double holography. Now, in that paradigm, there's a modification to the RT proposal to accommodate that end of the world brain in the bulk. And basically, so this is something I'll refer to as a semi-classical island rule. So we basically modify our homology condition to allow for, on top of the R from before, which is the subregion in the CFT, to allow for subregions I on the brain as well. And so that's how I would compute an RT surface with an end of the world brain in the bulk theory. And that can actually be viewed from the perspective of the brain world as a quantum extremal surface calculation. So the bulk RT is the brain world QES. If I happens to be empty for whatever the minimum configuration is, then that's one thing. But if I is non-empty, then that in the brain world that would correspond to these islands showing up. And this is something that we use extensively to try and understand the significance of the bath. So the first set of papers was really, if I had to kind of summarize what they were about, it was all about deforming the bath in some way, breaking the symmetries or adding some sort of deformation. So these were papers with Elena and R&D collaborators. I'll focus on the second paper here. So what do I mean by deforming the CFT? Well, let's start with Einstein plus scalar. This time I actually do want to have classical back reaction involved. So this is my action, and I want to take M such that the dual scalar operator is relevant, which means that the conformal dimension is less than the number of CFT dimensions. And that corresponds to a negative mass squared. But that's fine in ADS because scalars in ADS are allowed to have negative mass squares as long as they're above this thing. Now, when I add this scalar to the bulk, what I'm doing in the CFT is I'm adding a term to the action of the CFT that looks like this integral over some source, phi naught, times weighting this operator O. So this is a relevant deformation of the CFT. And when you add a relevant deformation to a CFT, that triggers a renormalization group flow, where you flow from some UV ultraviolet CFT in the space of couplings towards some infrared CFT. And the way that this is often viewed is that the bulk geometry corresponds to that flow. So this ultimately goes by the name of holographic renormalization group flow.
Can I ask a quick question?
Yeah.
This is for theta equals 0 now, all of it?
Oh, right now I'm not including brains yet.
Yeah, so, because you flashed this relationship between the conformal dimension and the mass of bulk scalar fields before. Does the BF bound change at all if I add end of the world brains in the bulk?
Yeah, I'm not sure if it changes if you add an end of the world brain that has a non-zero tension. I wouldn't be shocked if it does, but I'm not sure. If it has a zero tension though, I think you should be fine because that's just going to be like a probe that you're adding to the system. And that's what we'll end up with. We'll only work with a probe, right?
But possibly some of these windows, because if I remember correctly, there's this negative mass window and there's a positive mass window, and they roughly correspond to different boundary conditions for my bulk.
The negative, yeah, there's like so because it's I'm gonna set L to 1 because it's this.
Yeah.
I can try to, so if I set some mass squared, that's one thing, and I just fix whatever mass. But for each mass squared, there's 2 deltas. That's what I think you're referring to, right? Because if I solve for delta, I get 2 reads.
And then unitarity imposes these sort of restrictions.
So I think the BF bound, I don't remember exactly where it comes from. I think so that comes from stability.
Unitarity and like normalizability of like bulk fields, I think.
The BF bound, I think that's just you don't have an exponentially growing mode
Which
in
is normalized.
ADS, right? Normally you say, if I have a negative mass squared for a scalar field, I get exponentially growing modes. In ADS, that's modified, and the criterion is not mass squared equals 0, but there's negative. That's the bound that separates the exponentially growing modes from your usual oscillatory.
Unitary is something that you can also do on top of that as well for the.
Unitary gives it 1/2.
Yeah.
My only question was if any of that story changes if I add an end to the bulk.
I guess it would be about what the sign of your Euclidean action ends up being. I think with the probe brain, it's definitely not, because on shell, the action of a probe brain is just going to be 0. It might with if you have like a finite tension. I don't know. That might be that might be like a nice calculation.
Thanks.
Okay, so for concreteness, I'm going to consider the following ansatz, and 3 D equals 3, delta equals 2, for my bulk geometry and my scalar field. So I assume my scalar field has some radial profile, and my metric looks like this. The F has some simple root at R equals R plus, so this actually corresponds to a back-reacting ADS black hole. And if you assume these ansatz, then your PDEs, which are Einstein plus scalar and Klein-Gordon, reduced to some definitely nonlinear, but still solvable, at least numerically, set of ODEs. So you can actually solve for what this metric and scalar field are numerically. Now let's try and add in an RS brain, a probe RS brain to be specific. So we'll isolate a component of the transverse direction, just take x1, and we can just put in an RS brain at x1 equals 0. And that's going to be some surface of 0 extrinsic curvature. Furthermore, the scalar field is still fine because it'll just automatically satisfy a Neumann condition with that brain. So it still satisfies the boundary condition. So you can still work with the same classical configurations that you have without the brain. So this sets us up to do that sort of thought experiment with the eternal black hole, where we can calculate those page curves, those eternal page curves. One more point about the bat. There's now two parameters in the bat. There's two parameters in the bat. The first is nu now. It's the strength of this deformation. So basically you have some source phi naught, which you can pull out of the asymptotic fall off of the field. And you also have the temperature of the CFT, which corresponds to the black hole temperature. And you can take a dimensionless combination, which is just the ratio of the two for d equals 3 and delta equals 2. And that's going to tell you how strong your deformation is. If this is 0, then you have no deformation, ergo you're going to have just an ADS black hole with no back reaction. But if you turn this on, if this is non-zero, then you'll have, that corresponds to having back reaction in the bulk. We also need to be careful with R. We can't take it to be too close to that interface between the bat and the brain, so these lines here. We want it to be somewhat far away. If you take it to be too close, it turns out that your entropy curve just ends up being flat. But so with that in mind, we chose our R kind of carefully, and we were able to, we numerically computed these page curves. So the dashed line is for 0 deformation. This is just what you would get if you had no deformation of the bat. And this solid line is if you do have a deformation, where this is just some number that I chose. And you can see that the page time does look different. So qualitatively it doesn't look different, but quantitatively it does seem to change. And one thing that we saw, we were kind of limited in our, we were doing numerics, so ultimately there's only so much you can do with numerics as far as actually seeing what the asymptotic behavior of something is. But we found that roughly the page time appeared to monotonically increase as you dialed the deformation up. Okay, so let's now talk about the role of this massive graviton. So in RS, there is a limit in which the mass of the graviton can be taken to be 0. And it corresponds to taking that tension T to saturate that critical bound. So in this paper of Hao, Gang, and Andreas, what they found was that if you do that, in that limit, the page time appears to blow up, the page time that you calculate using this bulk RT surface. And that seems kind of troubling, because you lose your page curve as coincidentally as the graviton mass goes to 0, but we want the graviton mass to be 0. Now, there was kind of around the same time a proposal that if you have a theory of massless gravity, that should maybe furnish a flat entropy curve. So it's by these authors. In particular, I want to highlight to Raju, who would become a collaborator. So this principle is something that they refer to as the holography of information. And the rough idea is that basically by the time you're able to even do this thought experiment, you're actually, in some sense, holography can do better than just giving you a page curve. Like, what you would expect is that if you have access to some boundary degrees of freedom, you should actually know everything. So you should just see like a flat curve. That's like roughly the intuition of their argument. But the main point I want to emphasize, the important thing that's relevant to us is that they have a proposal for what an entropy curve should look like in a theory of massless gravity. And so that's what we wanted. We got this collaboration together, including several people at UT, with the goal of understanding the connection between the brain world, graviton's mass, and this page curve. And I'm going to focus on our first paper, where we actually try and see if we can get some sort of flat entropy curve in this setup of brain worlds. So you can introduce a massless graviton in RS by actually just adding a second brain here, second RS brain, which is this hashed one. And you go through the same procedures before integrate out the bulk degrees of freedom up to the brain to get some effective action for the brain world. And you get you get a graviton, a massless graviton. You also get massive modes as well, but the important thing is that there is a massless graviton. And so we have this sort of gravitating universe coupled to another gravitating universe as our brain world theory. In the bulk, we have this wedge. The boundary theory is essentially a CFT that lives on this solid red line, which is a codimension 2 defect. So that equivalence between the bulk and the boundary has also been referred to recently as wedge holography, or codimension 2 holography. So the simplest metric with some sort of horizon where we can try and have some semblance of that thought experiment from before that's compatible with two brains is this black string metric, which is written here. With this metric, you can plug it in to those RS equations determining the embedding of the brain. And all you get is that, you can just take constant mu, constant angle slices as your brains, your RS brains. And so essentially what the brain world looks like, so this is one side of the exterior, this is just one side of the geometry. There's in principle another side via geodesic completion. And essentially what the geodesically complete brain world looks like is two black holes that are attached to each other here and also attached to each other here. You can imagine them wrapping in a cylinder, but these blue lines are actually supposed to be viewed as identified with each other. So the entanglement entropy is still computed by some bulk minimal surface. Because you have this other end of the world brain, you also need to have some sort of boundary condition on the surface at that brain too. Now, we made a choice here. Our choice was that it should be a Neumann boundary condition at both brains, so as to not break disinvariance. Because if you specify a fixed point at which this bulk surface should end, that will break. We view that as bad because it would seem to break disinvariance. It would set like a hard point in your brain world. And so doing Neumann at both brains is actually consistent with what's done in the semi-classical island pool with just one brain. But so we then parameterize our surfaces as so keep t and x fixed. I want to compute entropy at some fixed time. This is a typo. We don't keep x fixed, but x ultimately contributes some overall prefactor that doesn't matter in the calculation of the area. You keep t fixed because you want the entropy at some time. And then we parameterize u as a function of mu. This is the equation you get for the bulk surface, and these are the boundary conditions at the two brains. Mu equals theta 1 and mu equals pi minus theta 2. So the minimal extremal surface you get when you do that is always the horizon. And there's literally no other surface that satisfies those equations simultaneously. And that's true for all time, so you conclude the entropy is constant in time. This is not the same as the page curve. This is not the same as the island populations. This is more consistent with some of, in particular, Sugrat's ideas about how Hilbert spaces don't factorize in the theory of gravity with some sort of Hamiltonian constraint. And so this idea of like factorizing the Hilbert space of some gravitating universe seems kind of iffy from that perspective. And so the surfaces themselves would, in the brain world, the surfaces themselves correspond to these green dots, and you do have these like green wedges between them. So one more thing I want to just note, like I said, we made a choice about the Neumann conditions. You can also say, well, I want to compute surfaces that have Dirichlet conditions on the brains. While we didn't do that, these authors did do it that way, and they actually got a page curve when they did that. And as a matter of fact, there is a type of surface with some Dirichlet condition you can compute, which doesn't seem problematic to us, which we did, which is a surface that's fixed to be anchored at this defect here, that's between the two gravitating universes. And we also So it depends on the actual tensions of the two branes, but roughly speaking, if the two branes have fairly large tensions, near critical tensions, you do get a page curve. As you dial the tensions down, there's some weird things. There's a point where you no longer get a page curve, and then there's a point where you actually no longer even get finite surfaces that end at like finite points in the book. But and that actually prompted us to further study the phase structure of these sort of surfaces, which we called left-right entanglement surfaces, more thoroughly in the one brain setup. But yeah, so the boundary conditions do seem to be important too. Okay, so just to wrap up here, overall, boundaries seem to be a pretty useful tool to like play around with these toy models of semi-classical quantum gravity. Not only do they make the dictionary richer by adding these new entries or changing entries up, like the reflecting geodesics, but they also seem to, they can also form the basis of these nice toy models to try and poke at long-standing problems and puzzles like black hole information. Just as a note to the present and the future, after doing a lot of this work, I got really interested in trying to understand boundaries purely from the conformal field theory side. So actually just within CFT, a truly generic understanding of the space of boundary conditions is not really too clear. It's well known in certain classes of theories, like rational theories, but in general, it's not as known. But knowing about such boundaries can have nice applications to problems in condensed matter systems with defects, impurities, or if you also care about the world sheet view of D-branes in string theory, you would care about boundary states in CFT. So, but that's more as like the general note of what I'm interested in, what I'd be interested in the future. But overall, that's all I've got. So thank you for your time.
Questions from the general audience? Oh, we have a big general audience. Any questions? Okay.
In the picture where you got a flat page curve, the entanglement entropy of what exactly are you calculating here?
Yeah, so it's probably clearest from the CFT perspective. Actually, no, I think I have it.
There's no CFT here.
There is this CFT in like wedge holography that lives on the defect. Yeah, so there's this one. So it would be the entanglement entropy of that with its thermal field double. Because I technically have in my full space, I have the red and I have the blue. So this is like some disconnectivity. So it's the entanglement entropy of this with the blue.
So this looks very different than the picture you showed before, where the region exists in both sides.
Maybe that's yeah, I guess.
Well, not here. If you go back to the kind of inherent feedback. Yeah, that one.
This one.
Yeah, your region art.
Yeah. I mean, here it's a region in the non-gravitating bath. It is different, but I mean, the goal of considering that like two-brain setup was to try and get rid of this bath in the first place and see what would fall out of applying the rules of double holography to the resulting configuration. So, but yeah, I mean, it's definitely different from this picture. That's for sure.
But the result is somehow not that much different from the place we started way back, which was just an ABS black hole without a bath, without any of this stuff.
Just vacancy hopping.
What?
Like
Yeah, you just
are.
have constant entropy because, any radiation that, was emitted bounces off of the boundary and
Right.
comes back, and so you just get a constant page curve. In some weird sense, the picture you were flashing towards in is just a double
Yeah.
of
Two are in
that.
equilibrium with each other?
Yeah.
Yeah.
I mean, and the entropy itself is
Exactly.
computed by the area of the horizon, so it's literally,
that's right.
it's
Yeah.
literally vector mapping, I guess.
Yeah, exactly.
Yeah.
Okay, Gabe?
Yeah, I had a very naive question which just occurred to me. So if you want to study black hole evaporation in ADS, instead of coupling to a bath, why not just consider a small black hole in ADS? Is that just harder to analyze?
Like in terms of you have some canonical ensemble and, but then how, so like how would,
Well, I just mean because a small black hole can evaporate.
well, evaporate in the sense of there's the Hawking page transition when you dial the temperature down. But I think if you want to recreate the idea, the basic setup of black hole information, what you want is a black hole that is able to like dynamically evaporate out degrees of freedom, right? So isn't thinking about a state in like a canonical ensemble, basically you are coupling it to some heat bath at fixed temperature.
Okay, I need to think about this. I think I'm just confused.
Nick?
Just naive question. Was there a big picture takeaway from these code calculations? I get a flat page curve for Neumann boundary conditions and a realistic page curve for Dirichlet. I imagine that breaking different variance is important generally. Or?
Yeah. I think one of the takeaways would be that, well, one could argue, and maybe I guess I would argue this, that breaking diff invariance and introducing that Dirichlet condition is how you get the page curve.
Generally.
Yeah.
Generally, yeah.
Yeah, or maybe that's the statement you would want to make more generally. I kind of feel a little more conservative about it in the sense that I personally prefer making these statements mainly in the context of these higher dimensional brain worlds. But you could also view it as like maybe this actually signals something important about like that Dirichlet condition in general setups.
Yeah, thanks.
And breaking different variants.
Yeah, also just a comment on Ian's question. I think your question was about like creating another black hole and like equilibrium between the two black holes. I think by the double holography picture, you already have, and by the foliation, you already have a black hole on the boundary. That's what we're referring to as a non-gravitating bath. So that's like the connection between the black hole on the brain and then the black hole on the boundary. So that's where you create the equilibrium. You already have another black hole on the boundary.
Okay.
So yes, that's I don't know if that answers your question. I just felt like this is something that.
Thanks.
Any more questions from the audience? If not, we thank Sanjit again.